My dear student, colleagues, and all the viewers who are watching this program live from Facebook page and YouTube channel, I would like to welcome you all to our International Physics webinar. So, good evening to all here in Bangladesh, and very good morning to all those who are watching this from this webinar live from USA. So, hope you are well and safe from Corona pandemic. So, as we know that we are staying in a Corona pandemic situation, and the situation nowadays becoming worse in our part. So, we have to follow our health rule. So it's very difficult for us to continue our normal academic program inside the campus. So we have to start our online program. I think you have already come to know that the Department of Physics, Pabna University of Science and Technology has started its online program, including online international physics webinar. We have successfully completed our 194th international physics webinar, and it's our 195th international physics webinar. So, today I would like to welcome you all to a joint session between our Department of Physics, Pabna University of Science and Technology, and Department of Astronomy, the University of Texas at Austin. And we have with us here today Dr. Mike Boylan-Kolchin, Professor, Associate Professor, Department of Astronomy, the University of Texas at Austin, USA, and he has already connected with us. So I'd like to welcome our speaker. So good morning and good evening to here. So thanks for accepting our invitation. And it's my honor and privilege to host you in our international physics webinar. So before going to you, I would like to introduce you with all of our students and viewers. So, dear student and viewers, I think you have already come to know the title of this today's international physics webinar. That is very exciting: the ages of astronomy from cosmology and stars. And our speaker is Dr. Mike Boylan-Kolchin, Associate Professor, Department of Astronomy, the University of Texas, Austin, USA. And we can see his short bio that Professor Mike Boylan is a theoretical astrophysicist who works on galaxy formation theory and its interface with cosmology. Recently, his research has focused on near-field cosmology, using detailed studies of nearby galaxies to address a wide variety of questions related to dark matter and galaxy formation physics across the cosmic time. His works combine numerical simulation, analytical models, and observation. And we can also see that he has completed his bachelor degree in astrophysics from Columbia University and PhD degree in physics from the University of California, Berkeley. So, and then he joined as a postdoctoral fellow at the Max Planck Institute for Astrophysics, Germany, in 2007, and he stayed there up to 2010. And he joined at University of California as a Southern California Center for Galaxy Evolution Fellow, and he stayed there up to 2013. And then he joined at the University of Maryland at the Department of Astronomy as a assistant professor, and he stayed there up to 2015. And then he joined as assistant professor at the University of Texas at Austin at the Department of Astronomy, and currently he also working as an associate professor at the same department at the University of Texas at Austin. So he has a lot of publication in different international journals, and his citation is more than 12,000, and H index is 55. So thanks for all of your questions. And it's time to go to our speaker. So, sir, I'd like to welcome you again. It's your time, sir. You can start your session. And the viewers and students, you can join with us by using this link, and you can ask question by commenting in Facebook and YouTube. So, thanks and enjoy this exciting and interesting talk. Sir, thank you again. And it's your time, sir. You can start.
Thank you very much, and I really appreciate the opportunity to speak here. I think one of the bright lights of this whole pandemic situation has been that we're able to do a lot more interaction than maybe we wouldn't have before with places that are further around the globe. So I really appreciate the opportunity to speak at your institution. So I'm going to be, of course, I'm going to be talking a little bit about ages in cosmology and ages of stars, and trying to understand, do we have a consistent picture of our universe from the side of cosmology and from the side of stellar astrophysics. And a lot of this is motivated by the successes of our current standard cosmological model, the lambda cold dark matter model, where most of the universe today is comprised of dark matter and dark energy. But it's also motivated by a potential issue with this model, which is that the expansion rate we measure today is not the same as the expansion rate that we expect if we extrapolate based on cosmological measurements. So I'll try to talk about how that all fits in together. You know, I always like to start with a slide of the Hubble Ultra Deep Field because it gives us sort of context for these kind of studies and talks about how or is related to some of these important questions, because everything you see in this image, other than one or two small stars, is actually a galaxy. And all of these galaxies are at a variety of different redshifts, so they're a variety of different distances away from us. And the faintest, the smallest ones may be up to 13 billion light years away or so. That is, the light has traveled 13 billion years to get to us, according to our current cosmological model. But we don't actually measure the distance to these galaxies. What we measure is how much light has stretched on its travel from the galaxy to us. And so that mapping from the stretching of light to the age depends on the cosmology we assume. And so I'll walk through that a little bit as well. As a reminder, though, even the Hubble Ultra Deep Field is just a tiny portion of the universe. If you look and put it in context, it's much smaller than even the size of the full moon. So there's a lot of universe out there to study and a lot to explore and understand, which is, I think, one of the great reasons to get involved in astronomy and cosmology in the first place. Okay, so typically when we see things about cosmology, we see an image like this that tells us the universe started with some quantum fluctuations. There was a period of inflation. Then there was a time when the universe cooled off to the point where atoms could form. And at that point, the radiation that was present in the early universe was sort of unlocked and was able to travel freely to us. And that will play a big role in this talk. That's the cosmic microwave background. And then you have a timeline here that you see on the x-axis. So it tells us when the first stars formed, about development of planets and galaxies, and then that later in the universe, dark energy becomes important, and there's accelerated expansion. And so you see the timeline here has an age associated with it. And just like the issue I talked about with distances a minute ago, the age is also not something we can calculate directly. This comes from our understanding of the cosmological model. And so I'll talk a little bit about how if you vary portions of this model a little bit, this age may change, and that our understanding of this age is maybe a little less good than we thought it was a few years ago, potentially. So there are basically two ways to study the universe then, and I've just talked about them. The first is sitting where we are and looking at galaxies that are ever further away or at ever larger and larger redshifts. So that's this backward in time way, starting from the very nearby universe and going outward. We can also study the universe forward in time, which was for the previous plot, which is basically starting from the assumed initial conditions and then running the laws of physics forward. And so what I'd like to talk about is how consistent are these pictures of the universe's evolution. This shows one sort of way to think about this of the sort of backwards approach. The backwards approach being starting where we are today and looking backward in time. And it tells you how our reach in terms of how far back we're able to look has improved in the past 30 years or so. So if we ask what was the status of the most distant, our understanding of the most distant galaxies 30 years ago, all we really knew about was galaxies that were in the universe at around the epoch when the universe was half its current size, which we'd call a redshift of 1, or around 6 billion years into the beginning, after the beginning of the universe, maybe almost 8 billion years ago. The Hubble Space Telescope made some dramatic improvements, and so that allowed us to see galaxies that we're at a redshift of 4. So a redshift is that factor that the light has been stretched. So the universe was a factor of actually 5 smaller at that time. And then with further observations from Hubble, either deeper observations or including different filters in the near infrared, we've been able to reach back much further. So by 10 years ago, we've discovered galaxies that came around maybe just 500 million years after the universe started. And that's a big difference as opposed to 6 billion years. And our hope is that in a few months, the James Webb Space Telescope will launch. That is an infrared observatory, and that will push back even further, hopefully studying some of the very earliest stars and galaxies in the universe. So the picture that we have of the universe is that it's been expanding and cooling since the Big Bang. And this sounds maybe trivial today, but this is really a fundamental observation about our universe, and kind of amazing that we're able to understand it. I think the best way that we understand it is with this cosmic microwave background. So I'll just spend a minute talking about what this is. If you observe the sky at radio frequencies, you find that in every direction you receive radiation, and that radiation has a black body spectrum. That spectrum has exactly the same characteristic temperature in every part of the sky, basically. Well, not exactly the same, okay? So that temperature is around 2.7 degrees Kelvin. But if you take away the mean temperature and you say, are there any variations, you find that there are variations. There are variations at the level of tens of microkelvin, okay? And so that's what this image is. This is showing you the temperature of radiation on the sky from every direction around us. Not the average temperature, but the difference from the average temperature. So you see hot and cold spots where the maximum deviation here is less than 1 degree Kelvin. It's actually only a few hundred millikelvin probably on this scale, or sorry, microkelvin on this scale. So this is the leftover radiation from the Big Bang, the cosmic microwave background. And the idea was the Big Bang was very hot and dense. As the universe expanded, that hot and dense universe cooled. And as it cooled, that meant that at some point it was possible for atoms to form rather than being ionized by all the radiation that's around. And that happens at about 380,000 years into the evolution of the universe, when the universe was about a factor of 1,000 smaller in size than it is today. And so once the universe has formed atoms, all the hydrogen is locked up in atoms, then light can travel freely to us. And that's what we're seeing here. We're seeing the patterns of hot and cold spots on the sky, which are related to slight overdensities or underdensities in the distribution of matter and energy at those earliest times. And so this is sometimes called a baby snapshot of the universe. That's, I think, fairly accurate. But more importantly, it contains a tremendous amount of information about the physical conditions of the universe at that time, and it allows us to understand a lot of properties of the universe. Okay, so the universe has been expanding and cooling. Since the universe is expanding, the matter and the energy in the universe is getting diluted because of that expansion. And I have to have an asterisk there because that's true for everything except dark energy, and I'll talk a little bit about that in a minute. So the idea is basically we have the same amount of physical matter. Matter isn't being created, but as the universe expands, there's more volume for that matter to occupy, and so the density is dropping. And so normal matter just drops off in proportion to the volume. If I stretch the volume, change the volume by a factor of 2, I change the density by a factor of 2. The volume goes up, the density goes down. And if we really think about what that means, it means that every side of a cube is increasing by some factor. We call that factor A, the scale factor. And so the volume goes like the scale factor cubed. Okay. If we think about radiation, it's not just that the number of particles is constant and the volume is increasing. We also have that the wavelength is basically being stretched out. So we have that radiation drops off faster in density in terms of this scale factor A. So if we're thinking about this, what does a scale factor mean? It really tells us, look, we have a grid here at different times. On the left, I have very early times, and I'm going through expansion here to later times. You can see here that they're the same number of grid cells in each one, but that means that the grid cells are changing in size. A tells you the relative size of these grid cells at each time. Okay. And if we look at the energy density of space, this cosmological constant, it actually remains the same as energy expands. So there's just the same energy per unit volume at all times in the universe. Okay, so the universe isn't just expanding. You might think that if the universe is expanding, it makes it harder for things to clump up. That's actually true, but gravity is very strong over large scales, and gravity is able to operate. So the universe is expanding and it's cooling, but it's also clumping up because of gravity. And I thought I could show a video that basically shows how this works. The video will show you a portion of the universe that's been simulated with a large numerical simulation, so millions and millions of hours. And what you see initially is fairly smooth distribution that becomes lumpier and lumpier over time as gravity starts to operate. So on the left, you see the dark matter portion of the universe. On the right, you see the gas in the universe. And you can see that the universe starts to get lumpier and lumpier as time goes on. So initially, there's very little difference in density from point to point in the universe. As the universe expands and matter starts to clump up, that becomes no longer true. So we see that portions of the universe with lots of matter get even more matter. Portions of the universe with less matter end up with less matter. So sort of sometimes people talk about this as the rich get richer and the poor get poorer in the universe as well. And so this is a result of gravitational instability. And what you can see here is the picture we have of how galaxies form within this universe as well. The dark matter provides the gravity for the normal matter to fall into. And then once the normal matter is in there, it can cool, collect up, form stars. You actually see stars exploding and black hole feedback in this kind of image. So this is these explosions that you see are sort of inputs of energy, very impulsive inputs of energy as a result of the evolution of galaxies. I won't run this for the whole simulation time, but you can see that already this is a very different looking distribution of matter than what we had initially. Initially, the matter was very well spread across this volume, and now it's much, much lumpier in the end. So, right. So the universe has been expanding, cooling, and clumping since the Big Bang. And so if we want to understand this, we have to get sort of at the physics of how this is happening. So how fast the universe is expanding depends on the kind of matter and energy in it. How much that matter and energy dilute depends on the kind of matter and energy. So like I mentioned, radiation dilutes differently faster than regular matter because not only is it getting diluted in terms of number of particles, it's having its wavelength stretched out, so its energy is dropping that way as well. And we have the equations that can explain all this. So basically, if you tell a cosmologist what kind of matter and energy there are in the universe, and how much of each type of matter and energy there are in the universe at some time, we can make predictions for all other times in the universe about how much matter and energy there are and how fast the universe should be expanding. So I'll do that a little bit here. There are some important components. There's this scale factor, A. And again, this is just the size of the universe scaled to the size of the universe today. So if we say the scale factor is 1/2, it just means that the typical distance between points evolving with the expansion of the universe would have been 1/2 as big as it is today. And that's related to the redshift of that galaxy by a straightforward formula. So we care about this scale factor, the expansion rate, which is how the scale factor is changing with time, and a different version of the expansion rate, the Hubble parameter, which is how the scale factor is changing with time, but the logarithmic derivative rather than just this standard derivative with respect to time. So the Hubble parameter is very important because it tells us about how the universe is expanding. Okay. And the most important equation we have in cosmology is the Friedmann equation that tells us how to relate the expansion rate of the universe, this Hubble parameter, with the matter in the universe. Okay, and it just says that the expansion rate squared is proportional to the sum of all of the densities that are out there in the universe. So the expansion rate depends on the density, basically. And here, when I talk about the density, I want to consider everything that's in the universe. So it could be dark energy, could be dark matter, could be neutrinos, photons. If you can find some other form of energy or matter, we should definitely include it in there as well. Okay. And so if you remember, how these evolve with the expanding universe depends on the scale factor. This dark energy is constant with scale factor. Dark matter and baryons are non-relativistic matter, so they just scale with the volume or the scale factor cubed. And photons scale like the scale factor to the fourth power. Neutrinos are a little bit funny because sometimes in the early universe they behave like photons, and in the late universe they behave like normal matter. And so I've kind of colored them in multiple color there to sort of indicate that. So basically, my point here is if you know what's in the universe, you can know its expansion history, because the expansion history just depends on the matter that's in the universe. An alternate way to write this is just to write the expansion at some time as the expansion at the present day, and then the fraction of the total energy. So rather than the density, you just write the fraction of the total energy density that's in some kind of given component. That's this omega here. Okay. So right, we can. How do we actually measure these kind of parameters? Well, again, this cosmic microwave background has been the source of much of this information. So basically what we can do is try to extract the physical information from this kind of picture and understand that the statistical properties of the hot and cold spots on this map, the temperatures of the photons, tell us about how much matter and energy fluctuated from point to point on the sky during this epoch of the microwave background. And the background physics is that at very early times, we have a universe that's dominated in its energy by the radiation. And that means that if everything is very ionized, we have the radiation scattering off of electrons very frequently. So the matter and the radiation are very tightly coupled. It's called a photon baryon plasma. And what happens is this plasma has a very high sound speed. It's something like 60% the speed of light. And so sound waves travel through the early universe in this plasma. And they travel in gravitational potential wells that are set by dark matter predominantly. And so there's a characteristic size on the sky that is picked up by these sound waves. And that's just the distance that a sound wave can travel in the early universe. And so this distribution of hot and cold spots tells us about the distance that sound can travel. And by knowing the distance that sound can travel, we can understand how much matter and radiation there must have been at those times. Okay. So normally what we do is we decompose this map into some kind of spherical harmonic distribution and do a power spectrum of this. So you don't have to worry too much about that. Really, this just tells you as a function of spherical harmonic multipole, L, which is just basically 1 over the angular size of a feature, how much variance is there on that scale. And so it tells you there's a very specific scale in this map. And that scale corresponds to a multiple of 200, or an angular size of about a degree. And so that's, again, the size in an angle that a sound wave could have traveled in the early universe. And so from knowing that, we can make a pie chart that tells us what the universe looked like 13.7 billion years ago. 13.7 billion years ago, the universe was 63% dark matter. It was something like 25% radiation and photons and neutrinos. And atoms were something like 12% of the matter and energy content of the universe. Then we take those equations that I talked about that say how do we go from the expansion rate and matter and density at one time to a different time, and we extrapolate to the present day. And we find that today we have dark energy is 68%, atoms are 4.9%, dark matter is 27%, and you don't even see photons and neutrinos anymore in this pie chart. They're too small to look at. And again, that's because their energy density drops off much faster than matter and than normal matter and dark matter in the universe. So this is the way that we take the microwave background observations. That tells us about the constituents of the universe at redshift of 1,000 when the universe was 380,000 years old. And we use those equations that I was showing before to look at how things evolved towards today. So another way to say that is if I look at these omegas, remember that's just what fraction of the energy density of the universe is contained in some component. I can look at matter, so that's cold dark matter and baryons. And for most of the universe's history, that was the dominant component there. At the earliest time in the universe, the radiation was the most important bit, and the radiation has been dropping in importance to today. And you see the dark energy, that's this sort of cyan line, has been increasing in importance till today. So again, the scale factor would be 0 at the beginning of the universe and 1 at the present day. So the present day is all the way here on the right side of this plot. Right, and so again, this Hubble parameter, or the Friedmann equation, tells us how to go from the densities to the expansion rate of the universe. If we rewrite this equation a little bit, we just take this first part of it. We can take the square root and rearrange a little bit, and it says that then dA over A times h of A is equal to the integral dt. So this is how we compute the time in cosmology. Again, really, it's just saying if we know that the universe was 0 size at some point, and we know how it's been expanding, and we know its size today, we can figure out how long it must have taken to go from size 0 to any other size in the universe. So that's how we go from this sort of evolution of the expansion rate of the universe to the age of the universe. And it's sort of like saying, if I know how fast a car has been going at all times, I can tell you when it left its destination. Similarly, if we know how fast the universe has been expanding over its entire history, and we know the distance that it's traveled, we can understand how long it's taken to get to that distance. So this is not a direct measurement of time, but within this model that we have, it is what the time would take to get to that point. So again, if we know the contents of the universe, we know how the universe has been evolving with time, and that gives us a way to compute how old the universe is. So I think I saw a question about whether the CMB alone gives us evidence for the Big Bang. And I think that it's maybe the best piece of evidence we have, or the one that really motivated people to think about this a lot. But I think it's not the only piece of evidence we have for the Big Bang. There's a lot of other pieces of evidence that are in strong support of this theory. I think one other cornerstone of our understanding of this is called Big Bang nucleosynthesis, which is predicting how many elements beyond hydrogen were produced at very early times in the universe. And the idea there is if the universe was at a much earlier stage, not now at a redshift of 1,000 or a scale factor of 1,000th, but at a redshift of 1 billion or so, the universe was so dense that atomic nuclei could fuse together to form helium and trace amounts of lithium. And we can take measurements today of hydrogen, helium, and their isotopes and ask, what does that look like compared to predictions if the universe had indeed been in this very hot and dense phase at very early times? And they agree remarkably well. So that Big Bang nucleosynthesis, I think, is another really good piece of evidence for this Big Bang model, just to name one. But the cosmic microwave background has certainly been a very important aspect of this. Okay, so if I go back to this previous slide, this tells us how long it's taken the universe to go from that initial point in time to any scale factor A. And one very specific important time is how long it's taken to get till today. So that would be an integral from the beginning, 0, to when the universe is its current size, which is 1. So that's the age of the universe, which we often denote T0 here. Okay, so that's basically the way we measure the age of the universe from cosmology. We understand what's in the universe. We use these equations to tell us how the universe had to have evolved, and that gives us an age for the universe. And if we plug the numbers in that we have from the best observations of the cosmic microwave background from the Planck satellite, we find that the universe is 13.797 plus or minus 0.023 gigayears, which is a gigayear is a billion years. So basically this tells us, if I look at this number, the universe is 13.8 billion years old with an error of only 23 million years on this very large number of 13.8 billion years. So the error is only 0.17%. And this tells us the universe is 13.8 billion years old, not 13.6. Not 13.7 even, not 13.9. It's really 13.8 billion years old, very well understood. Okay, so now an issue has emerged, though, in this model. And the issue is that we can figure out how fast we think the universe should be expanding today. And I've talked a lot about that. Based on the microwave background radiation and understanding what's in the universe at very early times, and then using our equations to calculate things moving forward. And if we do that, we find that the expansion rate of the universe, this Hubble parameter, should be 67 approximately, and these units that astronomers use. So the unit is kilometers per second per megaparsec, which is really just saying, if I go a distance, a megaparsec, which is like 3 million light years, if I go 1 megaparsec away, then a galaxy should be receding at 67 kilometers per second from me if it's moving with the expansion of the universe. And every kilometer further away I go, it goes an extra 60 kilometers per second per megaparsec. So that's the idea there. So this is the Hubble expansion rate, just in some astronomer units that would be measuring a velocity divided by a distance, and that's the Hubble parameter. Now, if we go out and measure the present day expansion rate using supernovae or other data, and I think one of the biggest groups that's been involved in this is Adam Rees's group at Johns Hopkins University. They are finding that the actual measured expansion rate of the universe is 73.2 plus or minus 1 in these same units. So this is pretty close, but it's not the same. It's statistically significant, this difference. So this is something like a 4 sigma discrepancy. So you wouldn't expect this to occur randomly. There's less than a 1 in 10,000 chance that would occur randomly then. So the conclusion is, unless there's an issue in one of the observations, so some kind of systematic error, then there's an inconsistency in our model. So remember, the basic idea of the way we've done this is we've taken observations at the very early universe of the matter and energy content then, and we've used that to extrapolate forward to measure the expansion rate today. And then we've measured the expansion rate today. And if we knew everything perfectly well, those two estimates would agree exactly right. They don't agree exactly. There's a little bit of a difference. And so that difference means there's something that's missing in our understanding of the universe. So here is one way to look at that. And this is called the Hubble tension sometimes. And so on the y-axis here, you see how much total matter there is in the universe today as a fraction of the energy density in the universe. And on the x-axis, you see the Hubble expansion rate. So this is the early universe measurement extrapolated to today based on the Planck satellite measuring the cosmic microwave background. It measures both the density in matter and the expansion rate, okay? And so it says that if that model is right, it should lie somewhere here. This is the measurement based on local measurements. This is the result based on local measurements of the expansion rate. So that doesn't depend on the matter density. It's not sensitive to that, but it measures the expansion rate of the universe. And you can see that there's a big gap here moving along the x-axis between the two measurements. And that's the idea of this Hubble tension. So one thing that you could do would be to change the contents of the universe a little bit. That would change the expansion rate, and that would change our predictions. And so there may be some way to match up the predictions from the microwave background with the observations today. And so one way to do that is to take this standard cosmology, which just says there's dark matter, dark energy, radiation, and neutrinos, and to add an extra little bit. So remember, normally we think of dark energy as something that's just a constant in time and space. And so it doesn't change as the universe expands. And so it becomes more important as everything else dilutes away. So it's only important in the universe's history at very late times. But people have been considering the possibility that there's also dark energy that was important at early times. So if you say that some small fraction of the energy density in the universe at redshift before the microwave background, redshift of 3000 or so, was maybe 10% of the energy density in the universe. So again, it's not as much energy density as matter or radiation, but there's a little bit of extra dark energy at that early time, this early dark energy. Then you can see that this doesn't change our predictions for how much matter or radiation there are very much, but it changes the cosmological parameters. So remember, this is that gap that we were seeing before. And if I include this early dark energy, I now actually find that there's agreement between the predictions of the cosmological model and the measurements that we see today. So by changing how fast the universe was expanding at very early times, we actually changed that prediction for how fast it should be expanding at late times. And now we can get agreement between the cosmological model and direct measurements of the expansion rate today. Now, we can also look at this in terms of the age of the universe. So remember, Planck gives you a very precise measurement of the age of the universe. That's this 13.797 plus or minus 0.023 billion years. And here I'm plotting the age of the universe on the y-axis as a function of the current expansion rate, h naught. Again, this shows you that you're very far off in terms of the current expansion rate using the microwave background versus the direct measurements today. But if I now change and say, let's include this early dark energy model, then I find that there actually is agreement between the early dark energy model and the observations today. That's what I showed in the last slide. And this changes the age of the universe pretty substantially in the place where the agreement lies. So I have to go from a universe that's something like 13.8 billion years old to a universe that's 13.1 billion years old, let's say. And so really what that says is that by changing the contents of the universe, I've changed how the universe is expanded. And that can make then agreement between the measurements of the universe's expansion at early times and at late times, but that's also changed how long it's had to expand between early times and late times. And so I've changed how old the universe how old we think the universe is. So again, that basically says that we just go back to this Friedmann equation, and this first bit here would have been what we had for our standard dark matter and dark energy model, and now we have to add on an extra term for this early dark energy, and so that changes the expansion history of the universe. So again, I just would plug this back in to calculate the time. So you can see that this changes the time of the time corresponding to any given redshift or scale factor in the universe. So if I change the cosmology, I change how the expansion rate goes, the Hubble expansion, and changing the Hubble expansion changes how the universe ages. So what it really says is the relationship between the size of the universe and the time in the universe depends on what's in the universe. That is, we know the size of the universe today is 1 in these scaled units, but then if we change the energy content of the universe, we don't know what time, or that changes what the time corresponds to. So every time, we looked at a plot like this before, and there's a correspondence, it says, between time after the Big Bang and redshift. So it says that 6 billion years after the Big Bang is redshift of 1, redshift of 4 is 1.5 billion years after the Big Bang, etc. The key point here is that this is not something that is true independent of your cosmological model. This relationship between redshift and time depends on what's in the universe. And if we change it a little bit, what's in the universe, we change this relationship. So this is kind of a problem, and so we want to have another way to measure the age of the universe. So what would that other way be? Well, we have a boundary condition, right? We know that the age of the universe better be greater than the age of the oldest thing in the universe. It would be kind of embarrassing if the universe was younger than the oldest objects in the universe. So the first low mass stars that form after the Big Bang, if they're low enough mass, they should still be around today. The lifetime of stars depends sensitively on the mass, and the lower the mass, the longer the lifetime. So things that are less than about 70% of the mass of the sun that formed at very early times should still be around. They shouldn't have evolved off of burning hydrogen in their cores for their main fuel. And so if we can measure the ages of the oldest stars in the universe, of these stars that formed as soon as possible after the Big Bang, we can set a lower limit on the age of the universe. And so a good place to find collections of these stars is in objects called globular clusters. So globular clusters are actually quite pretty objects, but they're very dense collections of hundreds of thousands or millions of stars sometimes. And they're very interesting because they're much denser than galaxies. So they have the size of the mass of a very small galaxy crammed into a much smaller size. We think they all form at around the same time, and there are hundreds of these around the Milky Way that can be studied in great detail. So these globular clusters are collections of hundreds of thousands of stars, and crucially, they all formed at the same time. And so if we can measure the luminosity and temperature of all of these stars in these globular clusters, we can figure out how old they are, because we can see when the stars started moving away from this main sequence of hydrogen burning that exists for stars in the universe. So this is a set of examples from a recent paper that I wrote with Dan Weiss at UC Berkeley about measurements for one globular cluster, M92. And you can see here are some age estimates from several different groups, okay? So one group thinks that that globular cluster is around 12.75 billion years old. Another group thinks that it's 13.06, maybe it's 13.25, etc. So there's some disagreement on the exact age, but the age is very close to the age of the universe in that early dark energy model, and it's younger than the age of the universe in the standard cosmology, in the Planck cosmology. So I'd say most of the measurements of these globular cluster ages are consistent with standard cosmology, and they may also be consistent with early dark energy. So what we've with that cosmology that's meant to explain the difference between the expansion rate measured today and extrapolated from early times. So if I say, what redshift does this age correspond to? When was 13.06 billion years ago? That's a redshift of 7. So that means the universe was 8 times smaller than it is today. But that's in the Planck cosmology. If I change to the early dark energy cosmology, it's very different. That's a redshift of 21. The redshift was 22 times, or the universe was 22 times smaller than it is today. So these oldest globular clusters, even if we can measure their age well, it says that in these two different models, they formed at very different periods of the universe's evolution. So I think one way we can think about this is if I take this globular cluster and I ask, when did it form? And I say, let's just say it formed 12.75 billion years ago. So that's shown here in this blue band. I can ask, what redshift does that correspond to? And you can see that these curves are different. For the standard lambda CDM model, I have this black curve. For the early dark energy model, the relationship between how long ago something was and the size of the universe is different. And so this time would correspond to a redshift of 5 in our standard cosmology, but it would correspond to a redshift of 10 in that early dark energy cosmology. Again, the universe looked very different at a redshift of 10 than it did at a redshift of 5. It had doubled in size over that period. If we look at the ages for the oldest galaxies, we actually see the same issue. And it's actually true for the oldest stars too. But let me take a look at the oldest galaxies. This is a set of work that tries to measure the age of the oldest galaxies in the universe. And consistently, those are around 13 point something billion years old. And in fact, some of them are old enough that their ages are inconsistent with ever being able to form in this early dark energy universe. That is, if early dark energy is the right explanation, the universe is too young to be able to host galaxies that are this old. And so this is one way we might be able to figure out whether this early dark energy model is a good one for explaining the Hubble expansion rate tension. So the other way we can look at this is if we know something at a fixed redshift, we can say that it corresponds to different times. So for example, the highest redshift galaxy that's known is at a redshift of 10.9. And you can see in the early dark energy model that would have occurred 12.7 billion years ago. In the Planck cosmology, that would be 13.5 billion years ago. So again, this is kind of emphasizing that idea that the relationship between how much the universe is expanded and how far something is away or when the light was emitted depends on how the universe is expanded between now and then. And if we don't know the cosmological model well enough, then we're not able to know that number well enough. So basically, my argument would be at present, there is an uncertainty of at least 4.5% in this relationship between redshift, or the size of the universe, and the look back time, so how old something is relative to today. That says that and that's just because we don't know those cosmological parameters well enough. This shows the fractional difference as a function of time, and there's just no way to get better than 4.5% in these measurements of the age of the universe as a function of how much the light has been stretched since it's been emitted. So that was kind of a lot in the last minute. So let me try to talk through what I think the important points are there. So the cosmological parameters of our universe are very well known if we assume that the lambda CDM model is correct. And those cosmological parameters include the age of the universe. So this is a question of precision. Within the context of a very specific model, how well are the model parameters measured? Now, there's another question of accuracy, which is not how well are the model parameters measured, but how well do we understand the model itself? So if we allow the model to vary, then what's the uncertainty in these numbers? So the accuracy, that's this sort of model-dependent number, would be much worse, okay? So the accuracy of the determination of cosmological parameters is less clear because our cosmological model could be wrong or it could be incomplete. So right now, the precision that's within the context of the lambda CDM model, the precision of the age of the universe measurements is 0.2%. We talked about that. But the accuracy is much worse, a factor of 20 worse than that. And that's 4%, again, because we don't really know whether the expansion history of the universe is exactly what it's supposed to be in the lambda cold dark matter model. The same thing exists for stars and stellar ages. And in fact, it's actually at a higher level. We can make a fixed set of assumptions about the properties of stars. So we can say, if I assume certain nuclear reaction rates and how the atmospheres of stars are structured, et cetera, and then I can say, based in that model, how do my measurements of stars tell me about ages? Well, again, the ages are precise. They're precise probably at the 1% level, but the accuracy is even worse, maybe 10 or 15%. And that's because we don't know the nuclear reaction rates particularly well. We may not know the distance to that star exactly, et cetera. So there's an issue of accuracy and precision in both cases here. So the path for improvement, I think in this case, is more data, okay? I guess the path is never less data, but here it's very important for more data, I think especially on the stars side. So the cosmology revolution has really made it the case that we can find these tiny discrepancies in expansion rates and think that they're a problem. And stars there's gonna be a lot of observations, large-scale observations of stars in the nearby universe. And so the accuracy of the measurements of stars may reach that same level, 5%, as cosmological observations in the next few years. And that might mean that they can provide a meaningful constraint on the age of the universe again that's more, that's at least competitive to the measurement that we get from cosmology. On the cosmology side, I think one of the things that we really need is a thorough explanation of systematic errors in the Hubble parameter measurements. So we understand how to make the predictions very well. The observations are somewhat more difficult, and trying to understand, is there anything we could have messed up in the observations, is extremely important. So my conclusions would be that this lambda cold dark matter model, where the universe is comprised of dark energy, dark matter, radiation, and normal matter, it's been remarkably successful at explaining cosmological observations, and we have sub-percent level precision on many of the parameters of interest, including the age of the universe. But one of the current issues in cosmology, the Hubble tension, indicates that the accuracy isn't as good. So remember, the way we got this tension is we said the lambda CDM model tells us how fast the universe should have been expanding at very early times. And then given what's in the universe, we can extrapolate to today. And the difference between that and what we measure today is almost 10%. Okay. And this leads to a fundamental uncertainty in how to assign a time to any given epoch in the universe in terms of its size or expansion rate. Okay. And I think the next decade will see improvements that may once again make stars competitive cosmological probes of this relationship between redshift and time. And I think that's, very important. So that was all I wanted to say today. So I think I'll stop there, and thank you very much for your time.
Thank you, sir, for your wonderful and exciting presentation, sir. And I think our students and viewers have enjoyed it a lot. So we have got few questions in inbox and in comment section. So if you allow, we can start our discussion session. So the first question I'll took from inbox. So is there any relation between cosmological constant and dark energy?
Yeah, that's a great question. So the cosmological constant is one possible form that dark energy could take. So dark energy is something that we refer to that basically causes accelerated expansion of the universe, and it could come from a variety of different ways. The cosmological constant is one way in that would do this, where really the energy density of the universe just does not depend on the expansion history of the universe at all. It just is independent of time. And so that's why it's constant. So the density of dark energy in that case would be constant with time. There are other models of dark energy where it changes a little bit with time. So how it changes as the universe expands would be a little bit different. So cosmological constant is sort of one possible form of dark energy.
Okay, thank you, sir. We have another question. So, how can we draw the CMB picture of the universe?
So how do we actually do that ourselves? It's definitely complicated. So the observations are done with satellites. So you have to go, outside of the atmosphere. You can do this from the Earth also. People measure this in the Atacama Desert in Chile, for example, quite well. Since you're measuring in the microwave regime, you want to be somewhere where you're outside of lots of water vapor. But basically what these satellites do is they just scan the entire sky and measure the intensity of the radiation. And then there's a bunch of steps you have to take from there. So you have to make sure that you've accounted for the emission of light from the center of the galaxy itself. Okay, the center of the galaxy also emits radio waves, and so you don't want to be considering that. Then you also have to account for the fact that the Earth and Sun are kind of moving around the galaxy, and the whole galaxy is moving with respect to the large-scale distribution of matter in the nearby universe. So you have to account for all of these effects. But once you've done that, you're basically making a map on the sky of the intensity that you're receiving just from this cosmological background at every point in the sky. And they've actually released all of their data. If you look up the Planck satellite, they have an archive, and you can actually go and download their data, the raw data and the process data. And they also have ways of making those maps yourself if you want to sort of, if you want to just go in and by hand make it yourself, which I've done once or twice. And it's I'm impressed with how much work they have to do, for sure.
Yes, sir. Thank you. So we have no question in the comment section. So now we need to go there. So the first question in comment section, here, what exactly does one mean by the quantum fluctuation?
Okay. So quantum fluctuations are this aspect of quantum mechanics, in that there's really no certainty in the position or the momentum of an individual particle. So in a sense, on very small scales, the uncertainty principle is telling you that there's that space-time and matter is fluctuating on these very small scales. So we sort of think of particles popping in and out of existence at all times on tiny scales, on very short time scales. And so that's actually where we think that all of the structure in the universe came from, because inflation actually takes these fluctuations that normally are confined to very small scales in the universe and stretches them out to actual sizes of galaxies and large-scale structure. So in our current model of cosmology, these quantum fluctuations that would be happening all the time in quantum fields in our universe on very small scales are actually ripped out to very large scales and form the basis of the initial overdensities and underdensities in the universe.
Sir, thank you. So we have another question. So can the force corresponding to expand the universe and not dominate the interatomic force?
Yeah, okay. So this is always an interesting question. I think basically the question is, if the universe is expanding, can we get to some point where the expansion actually affects an atom, let's say? And so that would pull the electron off of a proton or something like that. So I think there are a few different levels of explanation that one could talk about this. I think the first is a little bit more formal. So if we really say where do we believe the expansion of the universe actually holds, if we write down the equations, it's only on very large scales that these equations actually hold. So we don't think they hold this sort of in very gravitationally bound systems. So things that are held together by other forces, we don't think will get ripped apart by the expansion of the universe. You can now, even technically, an atom shouldn't be described by this this expansion. It's really something else. But if you did describe an atom by this expansion, you asked sort of how much would it be pulling at the electron, it would be something that's so small that it would never, ever be detectable. But it's not even clear you can really ask that question on the scale of an atom. That sort of Friedman-Robertson-Walker metric, the description of space-time expanding, only applies on larger scales.
Okay, sir, thank you. So we have another question. The current observation of invisible filaments of dark matter, these galaxies which are not connected by the gravity, is it point towards the fact that dark matter is not quantum particle but rather act as a single entity throughout the whole universe?
Yeah, so I'm not particularly familiar with those specific observations, but I think that our lack of understanding about dark matter and at some level means we should consider a lot of things. And so I'm not sure if this is exactly what you're thinking about the single entity, but it could be the case that dark matter acts more like a field than a particle. That is, if dark matter is made up of very light particles, then mostly those particles could act in a coherent state across very large scales. And so even though it would be maybe a single type of particle, it would act more like a coherent field. And so I think that's an interesting possibility to consider that a lot of people are thinking about.
Thank you, sir. We have another question. So does the influence of the gravity extend out forever?
As far as we know, the influence of gravity extends basically forever, but it drops off fast, right? It's a 1 over r squared force, just like Newton would say. And that's true in Einstein's gravity as well. So gravity does extend out forever, but the further away you go, the weaker it is. So eventually it won't be as important potentially.
Thank you, sir. We have another question. So does only CMB enough for Big Bang theory justification?
Right. So I think this is the one that I saw during the talk and tried to answer a little bit. And, I think this is where that Big Bang nucleosynthesis would be another pillar of our understanding of the Big Bang theory. But just the fact, one other aspect that would really show that I think the Big Bang theory works really well is that if we take these models that we have and we run computer simulations of the evolution of structure in the universe in this Big Bang model, we get things that look very much like the universe does on large scales around us. So I think there's many, many lines of observation and theory that agree with this. But the microwave background is certainly one very important one.
Thank you, sir. We have another question. So do quantum forms exist, and is the universe composed of quantum fluctuation at Planck scale?
Yeah, so that's a good question that I'm not sure I know the answer to. So quantum foam is basically we don't have equations that can describe the universe on the very smallest scales. There's a smallest scale where gravity and quantum mechanics should be important, both, and we can't describe the universe with our equations below that scale. So it seems plausible that quantum foam would exist. I don't think we can say for sure at this point. We do think that there must be quantum fluctuations at the Planck scale, the smallest scale, and in terms of size. But I don't think we are really equipped to understand exactly what that means for our universe, unfortunately.
Thank you, sir. We have another question. So will expanding a single entity dark matter act as dark energy over a large distance where the galaxies are not connected to each other by gravity? Hence, no need to considering vacuum energy as a dark energy.
Well, so I'm not sure I know the exact dark energy model or dark matter model that's being discussed, but in the standard Einstein expanding universe, there's no way for what we think of as dark matter to also act as dark energy there. And I think that's related to the idea we just talked about a minute ago of, the distance over which gravity operates is infinite. So galaxies may not be gravitationally bound to each other, but they're certainly gravitationally can interact, or that the gravity does work on those scales. And there's nothing that would sort of push them apart like vacuum energy. But we don't understand vacuum energy very well, so I think that it's always good to consider other possibilities.
Okay, so thank you, sir. We have another question. So we use the Friedman equation obtained from the EFE to obtain this data, but can we not use the same FRLW metric in the modified gravity theories and compare those data with the ones that we obtained from the observation?
Yeah, so that's a good question. If you change the theory of gravity, then you have to change what that Friedman equation would look like, right? Because the changing theory of gravity would change how the expansion rate of the universe interacts with the fields of matter and energy that are inside of the universe. So it may be that you'd have the same Friedman equation, but my sense is that then it would look very much like Einstein gravity, that you basically need a different field equation to get different. You'd end up with a different Friedman equation in different models of gravity, typically.
Thank you, sir. So we have another question. So is string theory correct, and can we explain? Can it explain everything?
So I guess this is probably above my pay grade at some level. I don't think we know if string theory is correct. I'm not even sure. String theory has many different formalisms at this point, as I understand it. I think it may be it may be the correct way to understand the universe at its most fundamental scales, but I think that certainly it can't explain everything now. I think that what it's sort of shown that there are some natural ways that we could understand the way gravity might come out of some forms of quantum mechanics if we apply it in certain ways, but it's not something that's really made any predictions that have come true, or even makes unique predictions in some sense. So I think that it's something where people are really struggling to find a way forward to figure out how to maybe constrain the model space and understand is it correct. But I think it'd be great to know if we knew if string theory was correct. Yeah.
Okay, sir. Thank you. So this may be the last question. So will expanding single entity dark matter will change AC as compared to dark energy?
Yeah, so I'm not exactly sure what expanding single entity dark matter is. If you're just meaning, one specific type of dark matter, like cold dark matter, it changes the Hubble parameter a little bit differently compared to dark energy. But if this is a different dark matter model that I'm not aware of, really what you just have to do is work out, as you change the volume of space, how much does the energy density of that fluid dilute. And so for normal dark matter, the Hubble parameter squared goes like the volume, just goes like the density. And so that goes like the scale factor to the -3 for dark matter, and is independent of scale factor for dark energy. So it looks quite different there. But I'm not sure if you're talking about a specific single entity dark matter model. I don't know exactly how that one would operate.
Thank you, sir. So thanks for your excellent presentation and discussion session. So before going to end, we have got one more question. So can I ask in the inbox? So does gravitational energy have any effect on dark matter?
Does gravitational energy have any effect on dark matter? So, I mean, I think it's at some level, absolutely. So I think, people mean different things by gravitational energy, but dark matter responds to gravity. And so any energy that is contained in gravity, dark matter will, dark matter will respond to gravity. And so dark matter has gravitational energy. Sometimes people think about gravitational energy as the energy, like the curvature of space-time itself. And there, yeah, everything responds to that curvature in some way. That changes the expansion rate of the universe. So I think that, in most ways, we'd think that dark matter does respond to gravitational energy. Now, if you're thinking of like a gravitational wave, you can ask, does that actually impart energy into dark matter? And they're probably, not at some appreciable level, but anything that interacts with gravity, which is pretty much everything, we think is responsive to gravitational energy.
Thank you, sir, for your wonderful presentation and discussion session, sir. As we have arranged this program to motivate and encourage our students in this corona pandemic situation, I think your this lecture actually will encourage a lot of our students to fall in love in this astronomy and astrophysics field. I hope in near future they might join in this field and will develop some things. As we know that about 95% of our universe is unknown, and that is dark matter and dark energy. So hopefully the next generation will solve that problem. So thanks again in helping us in doing such an important webinar and exciting webinar with you. It is a great opportunity for us students and viewers to interact such an famous scientist like you through online. So thanks again, and we would like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology, for giving us this opportunity to arrange such an important webinar. Bye for today.
Thank you.
And hopefully in near future we will arrange another webinar. And after the COVID situation, I will definitely invite you for a face-to-face session to our university and to my beautiful country. So bye for today. Have a nice day, sir.
Thank you very much for the opportunity. It was great to present.
Yeah. It's my pleasure.